Hi everyone. This video we're going to keep talking about entropy and give a little bit more detail on what's going on with it. So entropy we see is affected by several different things. So first one's going to be volume, right? If we increase the volume of our container, the molecules in the container are going to have more places to go, right? There's more positions possible for these molecules to exist in. So because of that, when we increase the volume of a system, we're going to see an increase in our entropy. Now the same thing's going to happen with an increase in temperature, right? The one thing I want to keep pointing out, right, if we increase temperature, the average kinetic energy increases. Always remember that, right? We've talked about that before with gas laws and everything else, but the kinetic energy increases with increased temperature. So because of that, again, different molecules are going to the molecules are going to go faster. They're going to increase in speeds, which is ultimately going to cause an increase in entropy. We talked about this a little bit in the last video, but I just wanted to reiterate that the physical states with entropy do play a role, right? So entropy is going to be biggest in materials that are in the gas phase because the different places that those molecules can exist is much greater than, say, in the liquid phase where they're more condensed, and even greater than the solid phase where they're locked into position. So if you're trying to figure out what system has greater entropy, less entropy, one of the quick ways to look is what are the states, right? Anything in gas phase is going to have a greater energy than things that are in the solid phase. So to kind of review, for the entropy in the molecular scale, entropy is going to be dependent on several things, temperature obviously being one of them, volume, and also those number of particles, right? We talked about this in the last video. The more particles you have, the more possibilities that those molecules can arrange themselves in different orders, therefore the greater the entropy. So I'm talking about second law of thermodynamics. This is kind of a big one we want to keep in mind. And the idea that the entropy in the universe is going to be continually increasing. So therefore, any spontaneous process, right, which we talked about being irreversible, the spontaneous process, the entropy in the universe will be above zero, right? It's going to keep increasing and going up. Versus a reversible process, it's going to equal zero. Now we hit the third law of thermodynamics, and this really comes down to absolute zero. Right? At absolute zero, we have no more energy in our system. We've removed all the energy. Everything is completely still. Nothing is moving. Because of that, everything is completely, truly frozen in place. At 0 Kelvin, we will say at 0 Kelvin, there's only one microstate. As a result, there is no entropy. Right? So all of our entropy values are going, in terms of entropy of individual molecules, are going to be positive, right? You can have a negative change in entropy, but at any given point in time, that S value is going to be positive because when you hit zero, you're at 0 Kelvin, right? We cannot go below that. So talking about standard entropies, we can look up these values just like we can look up the delta H's, right? If you remember looking in our textbook, we'd have the huge table in the back that has information on the enthalpy of various substances. The same things exists for entropy. So we can look up all of these values. They're all going to be in standard state, right? So if we see the little zero here, reminder that's going to be standard state. Standard state thermodynamics is at 298 Kelvin, right? 298 Kelvin, reminder, is different than STP for gas laws, right? STP is 0 Celsius, so 273 Kelvin. Standard state for all things in the thermodynamic world is going to be 298 Kelvin, right, which is just about room temperature. The other thing to consider, is that unlike with enthalpies have positive and negative values, and any elements that are in their regular state at room temperature. So, for example, right, hydrogen being a gas, oxygen being a gas, the enthalpy of all of those was 0, but entropy, because we're not at 0 Kelvin, is not going to be 0. All of these entropies are going to be positive values. The other thing I want to point out is units, right? When we were looking at entropy, these values are joules per mole Kelvin versus the enthalpy, the values you're going to see are in kilojoules. So we always have to be a little bit careful of our units when we're working in the thermodynamic world. Now, to calculate change in entropy, it's the same thing we deal with before. It's based on the number of moles. So if I see kind of sum of n, these are just those coefficients in the balanced equation. And then we can just pull the numbers up and do products minus reactants, right? So if we have 2A going to B, right, I've got, you pull it up, you can look at the entropy of S for B minus 2 times the entropy for A. Right? It's the same process as we've done before. It's a fancy equation, but it's the same thing, same process we've done before that we did with enthalpy. So now I'm going to challenge you. I want you to try to calculate, I apologize, this is a typo. This should say entropy. What is the standard entropy change for the combustion of propane? So you've got your delta S values there. For your standard values, I want you to try to calculate it, and we'll pause the video and see how it does when you come back. All right, let's look. So we want to do products minus reactants. So the first thing we have to do is actually write our equation. So we know combustion of propane is going to be C3H8 in the gas phase plus oxygen is going to yield carbon dioxide plus water. So if I balance it out, I have 3, 4, and 5 here. So again, products minus reactants. So 3 times carbon dioxide at 213.6 plus 4 times the value for water, so 118.8. So all of that subtracted my 1 for propane, so 269.9 plus 5 times my value for oxygen, so 205. When I do the math on that, I get 1,116 minus 1294.9. So I end up with a total delta S being equal to negative 178.9 joules mole. And that's it, right? All this should look very, very familiar to everything we've been working with in the past. All right, so hope this makes sense. Let me know if you have any questions, and thanks for watching.